Okay, let's start. Do you have any questions? All right, so last time we were discussing, right, about the Greeks. Basically, a broad definition, okay, would be the sensitivity of an option price or a derivative price right, with respect to some parameters, some underlying parameters. Okay, so our focus, or what we would like to focus on, basically is the Greeks of the call option, but just basically focused for discussion. But I'll quickly discuss, right, how you can generalize this to the put and some other, spread, right? And but beyond this, right, keep in mind that the idea of the Greeks applied to any kind of derivative, including, let's say, American option, for example, right? So first, right, let me show you the Wikipedia page where, right, they list the Greeks for the, let me see here, for the Greeks for the different kind of derivatives. Okay, you see this? So first of all, right, I just want to point out with the names. So you see, like here, right, these are all the kind of Greeks that Wikipedia list. And they're above and beyond what I told you, right? You have the delta, the gamma, the vega, the theta, right? These are the basic one. But then you see, like, they have this, oh, and what's a rho? I'm not seeing the rho here. But anyway, right, you see all this strange name, charm, veda, vana, vama, speed, zama. Okay, so again, right, just that you have as many Greeks as the number of derivatives you can take. So I want to point out, right, so here they list it out quite nicely. So this is the first order, right? So you got the delta definition, the vega, right, with respect to volatility, the theta, right, see a negative here with respect to the time to expiration, because again, right, time to expiration are always decreasing. Rho, right, with respect to the interest rate. Lambda is a strange one, you see now already, right? It's not listed up there, but lambda is some component, for some reason they say it's called elasticity. So basically it's the delta, right? But then you want to proportional it with the, multiply with the proportion of underlying over the value. Okay, so I guess I've seen this before in economics. It's called elasticity. Yeah, so they don't care for the change, right? They care for the percentage change. Basically, if another way to rewrite this, if you pay attention, is delta V over V divided by delta S over S, right? So it's really the ratio of the percentage change, right? Percentage return, if you will, of these two, okay? And epsilon, another one, right, is going to be the sensitivity with respect to a dividend, okay? So again, right, what's our focus? My focus, or the main ones I want to talk about is, vega, right, delta, theta, right, and rho, right? These guys are just kind of like, I want to let you know that there's something like that out there. And even, right, a little bit more exotic, this is a second order, right? The gamma is actually very popular. We will see the gamma, right? We will have to concern ourselves with the gamma. So gamma is important. But then, right, it starts to get interesting. There's a Vanna here for you, which is a cross derivative with respect to volatility. Or, another way for you to think about it is, why do you care about these kind of things? It's because delta as an object, right? Remember, delta is the sensitivity of the derivative with respect to the stock underlying, which is very, very important, okay? As I'll show you later. The delta is the number of shares you want to hold to have a effect called delta hedging. So to hedge your option, practically speaking, you just hold delta share of the underlying. So for that matter, you want to know, for example, the sensitivity of your position, right? How much you're holding with respect to the volatility, right? And so that becomes the second derivative, right? Like this, and that's given a name called Vanna, right? Here is the sensitivity, right, of the delta with respect to the time to expiration. Again, right, entirely practical, because I guess these two guys, at least, and you can see some other ones below, care for, right, the sensitivity of the delta, right? Delta now is an object, is sensitivity with respect to the underlying parameters, right? Volma, second derivative with respect to volatility. Veta, sensitivity of vega with respect to the underlying with the time, with the remaining time, so on and so forth. There's even third order, right? And beats me on this. I mean, I don't know why they care for this so much, but I know this, right? I mean, that's because of my lack of knowledge, not because like these are not practical. The one thing for sure is, if in the financial world, if there's a name for something, I think it has a point. So here, right, this guy has a use, okay, Zalma. But right, we will not focus on this. Just want to point out these guys exist. Something called color. Anyway, right, and then here's a good nice table, right, that I refer to, that tells you basically. So this is Black-Scholes formula, in case you don't recognize it. This phi right here, right, is what we call N, ND1, ND2. So D1 is LD plus, D2 is LD minus. Okay, that's a Black-Scholes put option. And here they list all the derivatives for you, right? Sorry, yeah, I mean derivatives as in like all the Greeks for you. All right. So for all intent and purposes, right, you can just go on here and look up the formula. But my point, right, is to, of course, not just to show you this and then call it a day, but we want to go deeper, right, into the aspects of the Greeks and how it interacts, right, at least with the basic ones. All right. Questions so far? So the goal, right? The goals for you is, first of all, to be able to, right, know, or like quote, right, the formula for like certain Greeks. All right. I would say that you want to memorize, if you ever like do something along this business, you want to memorize the name, like what does delta mean, what does gamma mean, what does theta mean, oops, what does rho mean, right? What else? What does vega mean, right? These things, again, I guess they don't mean much for you right now if you don't pay attention, but right, it's just like the part of the language that people use. So instead of saying the first derivative with respect to a stock, second derivative with respect to a stock, right? They say delta or gamma. So you want to memorize that. The second, right, is at least know the idea of how to perform the computation. Okay, for these Greeks. In other words, you know, suppose that like delta equals to nd plus. How do you get this? How do you differentiate the Black-Scholes formula and get down to this? Okay, not because like it's super important, like I said, right? Wikipedia has already made it for you, but for different reasons. I mean, Wikipedia is pretty reliable these days, so pretty much there should not be an error on those formulas. But you never know. At one point, there could be an error. And if you cannot perform the computation for yourself, then if you look at a formula somewhere, and let's say they have an extra minus, or they have some different symbols that you don't expect to be there. If you don't know the computation, then it's hard for you to check whether what they wrote makes sense, or simply they just make a typo somewhere, for example. And then third, which is what I guess I want to focus on more, is the meaning, okay? The meaning of the Greeks. So let me tell you, right, that when you look at the Greek, they're derivatives, right? They're derivative of something. So you want to look at the several, these are routine questions you want to ask. What are the sign? Is it always positive, negative, either? Because, right, some positive with derivative means it's always increasing. Negative means always decreasing, right? That's super important. Because, for example, like Vega is always positive for both call put option. That means that, right, the call and put option price will always increase with respect to volatility. That's a very important fact to know, right? Magnitude. How large are these derivatives? Sometimes there's no range, sometimes there's a range. And it's quite important because there's an implication, again, right? Because it's a sensitivity level. For example, is there any range on delta? Is there any range for value of delta? So delta is ND plus, okay? So N being the probability, right? N being the probability of the the CDF of normal. So the natural range of delta is between 0 and 1. Coincidentally, right, delta here is also positive or no negative. What that means is, right, if the underlying price goes up, then call option price goes up. That actually is not that strange, right? Intuitively, because call option pays you, right, to share with some strike level. So of course, if the currently the price goes up, you get more value for your call option. So this fact is there, right? Reinforcing what we know, but that's not super exciting to know. But here, maybe this is something that is natural or not, depending on how familiar you are with call option. But here, right, that what that means is if the underlying change by $1, the call option price can only change at most $1 or less, usually less, right? Because this is strictly. So the change, right, the corresponding change for $1 change in the underlying is less than $1 for a call option. Okay, so that's magnitude. Again, sometimes we can say something about this, sometimes we can't, right? But we want to pay attention and see if we can shift this information out of the formula. Beyond magnitude, right? Where does it achieve is max or min? Again, may or may not be able to answer this kind of question. But it's interesting to know roughly why. Again, right, you're looking at the sensitivity measure of your option. So if you're at a range where the sensitivity is at the maximum, then one movement of the underlying will cause a lot of change to your call option price, to your option price. Okay. But if you're at the minimum, you couldn't care less. It's almost like, does not respond. But again, this is all relative because, right, min here would, of course, with respect to what kind of magnitude. But still, right, I guess sign and magnitude are quite important to know. Achieving max, min, okay. But as you can see, right, these are a fancy way to say the question that you have learned from calculus 1, meaning that you reconstruct a function from information about its derivative. And by derivatives here, I do mean calculus derivative, okay? I don't mean the derivative finance. But basically, right, you see, the function we're talking about is the option price, right? And it's a very complex function, being a multi-variable function, right? It depends on many variables. So ideally, it's a complex object, so reconstructing it is hard. And you want to, right, the more information you have on the derivatives, right, meaning like the sensitivities, the more you can say what happens to the function itself when these guys move around, these parameters move around. Okay. Any question? All right. So the I guess here, right, maybe I would say 4-2, right, connection to the Greeks of the put option and all the spreads. Like butterfly, bull, bear, iron, whatever, iron condor, whatever, But this is just an easy extension. That doesn't take much time. The reason I say that this is because I say we focus on the Greeks of the call option. But if you remember, right, recall the Wikipedia page, they give call and put at the same time, right? But from call, you can easily know put. So anyway, right, we're going to do these 4 things. So we're going to go down the list and take a look at each and kind of remark on these 4 points. Okay. So start with the delta, right? Delta, of course, denoted by delta, which is the sensitivity of the option price with respect to the underlying. Okay. And you will see me sometimes write something like this. The reason is basically, right, this kind of express the idea that it's a sensitivity at any time. But of course, right, our present moment is at time 0 and it's a function of the current stock price. So this is just to highlight the idea that, in the Black-Scholes formula, the current stock price show up, and that's exactly the derivative we're taking with respect to. Okay, so 1, right, is item 1, already said is MD plus. 2, calculation, right? Remember that everything starts with the V call, right? Equals S0 ND plus minus K e to minus RT ND minus. So to differentiate with respect to S naught here, you need, right? So pay attention to, right, a product and chain rule. When you differentiate these, because the plus minus, right, are functions. of S0. Okay. The second one is when you differentiate the plus, okay, with respect to any variable. So here, differentiate this with respect to S naught. What you get, first of all, is the density function evaluated at S naught, sorry, at D plus. And then you multiply the derivative with respect to S naught of D plus. Okay, so that's the chain rule part that I was talking about. Okay, that's a chain rule. And third, after you work all these things out, it will be a complex expression anyway, a tedious expression, that's what I mean. The third part is you need to pay attention to one single identity that you will have to use, okay, if you ever touch this. And the identity is, let me see. The identity is S0, important identity, okay? I mean, important in the sense that you will see this again and again if you ever do the calculation. S0 ND plus is equal to K e to the minus RT ND minus. Oh, sorry, not N, right? N is wrong. F. FC. It's kind of amazing, right? This is, if you put ND plus and ND minus here, that's Black-Scholes formula. Of course, then it's not equal because the cooption is not 0. But when it at so at the CDF, they're not equal, but at the density level, they're equal. So that's like that. All right. So those are the calculations I want to highlight. The actual calculation has been done last time, so I won't repeat it. Okay. 3, right? The meaning. Okay, the meaning. So first, right, sign we already discussed. Right, delta is always non-negative. So if stock price goes up, call option goes up. Simple. Magnitude is always between 0 and 1. What this means is the change in the option is always no more than the change in the stock price. Okay. So by the way, right, I know notation can be a little bit weird here. This is the Greek delta I'm talking about. But by putting this together, I don't mean the Greek delta times V, okay? I don't mean that. I mean this is the change in V. So if you're confused, maybe I'll do a small delta here. I don't know. That's even more confusing, right? What notation should I use? This? Okay. So this is the Greek delta. This is change, right? In V. This is change in S. Okay. So what I'm saying is, because the magnitude of the sensitivity is bounded by 1, for $1 change in the underlying, you will have less than $1 change in the stock. Oh, sorry, in the option. All right. What about the max min part? So where is it that the what do you think? Where is the call option most sensitive with respect to the stock price? In what range? So here's a question: in what range of S0, right? that the call option is most sensitive in and by the way, right, let me put somewhere here in question 3. Among this guy, right, you can also, there's another idea called limiting limit. Let me just put limit. In other words, it may be interesting for us to learn what happens as we push these parameters to a very large value. May or may not make sense, all right, depends. For example, if you push the interest rate to 0, that makes sense. You push the interest rate to infinity, it makes no sense because the interest rate will never get, above, I don't know, 10%. That's already large, right? But so the limit here must be taken with a financial, right, point of view in mind, all right? So, but here, right? So let's take a look. If the option is simple, in this case, right, this is the call option, so it's simple. It is helpful to look at a payoff function, right? This is K. This is a stock price. This is S minus K plus, right? So it's basically, so one fact of life is that this line right here, right? So this is the payoff function. The line I draw right here is the option value. Okay, so this graph is a graph of the option value as a function of stock price, which is exactly, the Black-Scholes formula right there. This is just a graph of the Black-Scholes formula as a function of S, this guy, right? So maybe let me not do S minus K plus here, right? So this is just a graph of two things, right? The payoff function, so this guy right here is S minus K plus. This is the Black-Scholes. Okay. Anyway, what do you see, right? You don't need like to analyze the Black-Scholes formula very carefully to see that, right? The option value kind of is asymptotic to the payoff function as it goes to the 0 and as it goes to infinity. All right. In other words, what we see, right, is that observe that as, right, S goes to 0, V0 goes to 0, right? As the stock price goes closer and closer to 0, it's flat. But as S goes to infinity, of course, V goes to infinity. But another more informative way to say this is V call is going to be closer and closer to S minus K. That's this part. You understand? Because, right, as a stock price gets really large, be above K, then you're guaranteed that you're going to get paid S minus K, right? I guess maybe you should have a discount or something. So it's going to be e to minus RT or something like that. But, right, ignoring this part, the discount, suppose the discount is small, then the majority of the portion is just this, okay? So how does that affect our derivative? In terms of delta, what happens to delta as the stock price goes to 0? as the stock price goes to zero, you see that the delta is going to go to zero. There's no sensitivity there, right? If you are really deep out of the money, then a small change in the stock price will not lift the option away from zero. That's what it says here. So if you're deep out of the money, a small change in the option price will not move you out of the money. All right. On the other hand, right, if you're deep in the money, all right, sorry. So actually, I take this back. I think it's just S minus K. It's not S minus K e minus RT. I'll tell you the reason. It's S minus K because this S is the present S. So let me say S0, like that, okay? S0. So here you could say this, e to minus RT is attached to a K, right? But this is S0, okay? So not the whole thing like this, but the discount only apply to a K. So so in terms of delta, as S goes to infinity, okay, as you are very deep in the money, all right, you're very sure to make money, then the limit of the delta is 1. Okay, so if you're very deep in the money, then $1 gain in the stock price will correspond to $1 gain in the call option. Okay, that's what this says. And again, right, it's completely backed up by the picture of the PR function and the option value. And we also do the calculation to verify this. But any question here? Okay, so how do we do a calculation to verify this? Well, the limit, right? Let's say as S goes to 0 of delta is the limit as S goes to 0 of ND plus. Okay, and what's D plus? D plus, right, is, and by the way, because N is a continuous function, it's a CDF, it's continuous. So you can do this. So basically, it's about the limit of D plus as S goes to 0 or infinity. So D plus is what? R plus 1/2, right? Sigma square times T minus log K over S0 divided by sigma square root T. So, right, if you push stock price to infinity, right, or S0 here, right, that's the same thing. So I'll just take out a 0 here to make it consistent. So if you push S to infinity, S to 0, what happens? If you push S to 0, this guy goes to positive infinity, right? So natural log of infinity is infinity. So D plus goes to minus infinity. And what's the CDF of a minus infinity? Will be 0, because that's a probability that a normal less than something. So the probability of normal less than minus infinity is 0. Okay. Similarly, you see that the same thing happens when we push S to infinity. When we push S to infinity, right, what happens is this is N like this. But let's see, if S goes to infinity, then this guy goes to 0. What is the natural log evaluated at 0 or close to 0? Remember, the log function has this kind of shape. So close to 0, the log is minus infinity. Okay, the log is minus infinity. So this is minus infinity. With a minus there becomes a positive infinity. So that's going to be n of infinity. But what's n of infinity? Again, right? N is a probability that the standard normal is less than some number. So n infinity is 1. Okay, again, confirming all of this intuition. Any question? Okay. So part 4, relating all this to other kind of derivatives, right? What is the delta of a put option? Well, so first of all, right, you think, or you may think that we have to do the calculation again, or you just look up in Wikipedia, right? It doesn't matter. But the fact of the matter is, right, that between put and call, there's always an easy kind of extrapolation because of the put-call parity. That says, right, call, or rather be call, minus v put is right forward, which is s minus k. And you can deduce all your derivative from here. For example, right, if you differentiate with respect to s, which is the delta, then that means you differentiate this with respect to s, well, you see that's clearly 1. And so that means your delta put is minus of 1 minus delta call. But we know what 1 minus, right, nd plus is. If you do 1 minus, it just go to the other side of the normal table, which is minus d plus, like that. Okay. Question? And okay, so what do you observe here about the delta of the put? Very quickly, right? For example, the put, right, will be always negative, and its magnitude is bounded by 1 as well, which again completely makes sense, right? Because for the put option, right, the fact is negative means if the underlying price goes up, the put price goes down. Nothing surprising there. That's exactly what we expect. Moreover, right, the magnitude of the change in the put is no more than the magnitude of the change in the underlying. Right, again, this is completely expected, right? You could also take the limit, right, as you can also take the limit as s goes to 0 of delta put, and the limit, right, as s goes to infinity of delta put. Well, how do you see this most easily? You could analyze this expression, but you know, I'm a bit lazy, all right? And do what we did before, or you can just rely on this. So, right, this equation says it all. This says delta call minus delta put is equal to 1. So basically, right, remember, as s goes to 0, delta call is 0. So that means delta put must be minus 1. As s goes to infinity, right, then delta call is 1. then delta put is 0, which kind of is the opposite of the call option, right? Which again is very easy to see. Why? This is actually where you're deep in the money, okay? So a gain in the stock price, a $1 gain in the stock price means a $1 decrease in your option value. Conversely, right, a $1 decrease in the stock price is a $1 gain, right, in your stock. But your stock is almost zero, very small already. So I guess $1 loss in the stock price seems not sensible. Here, right, you're deep out of the money, right? The stock price very high. You have no chance to make money with your put option. So of course, any small change, right, in the stock price will not have any effect on your put option value. Okay. All right. Question on this. Okay. So the second object that's also very important is the gamma. Okay. The gamma is the second derivative of the call option or of the option in general with respect to the stock price with the underlying. Okay. So the formula, okay, for the gamma is what? So first you know the delta, right? Delta is ND plus. So actually you could just calculate the gamma, which is this, right? Gamma is the derivative with respect to S of the delta. So remember, right? It simply is FZ D plus times partial D plus with respect to the stock. And, right, it should not be surprising that it comes out to be FZD plus times 1 over S sigma square root of T. Right. And actually that you can see that from here, this is our D plus, right? If you differentiate this guy with respect to S, first of all, right, the minus log can be flipped around to give you the log of S. So log of S differentiate to 1 over S sigma square root of T, right here. Okay, so that's your gamma. So actually gamma calculation is quite easy as long as you remember what ND plus is and you remember, right, what the Black-Scholes formula say about D plus. Okay, 2, wait, I think that was 2, right? I forgot what 1 is already. Let me see what are the points. Oh, sorry, right? So I was talking about 2. No, now we'll do 3. So this is 2, right? This is 1. Two, 3. What are the signs of the gamma? Can you say something? Is the gamma of call option positive, negative, neither? How is it? No, look again, because what is this object? F is the density of a normal, right? And how is the density of a normal? Look, The density of a normal is always positive, right? So the gamma is always positive. Okay? The gamma is always positive. Oh, you're concerned about sigma. Sigma is a volatility. Yeah. One thing, right, is you can be sure is all our parameters are always positive because they are in some way they are financial parameters. It's a very strange thing if any of them goes negative. Okay, so gamma is always positive. Okay. uh, how does the what is the range of value of gamma? Can we say something about that? So, right, again, with range of values, we mean with respect to S, with respect to underlying, right? That's what we care for. With respect to underlying, right? Well, so first of all, let's see, right? Let's see what we can say. So first of all, right, this guy, so here's the deal, right? Can gamma be quite large? Can gamma be quite large? Of a call option? The answer is no. Why? Because what do we know about the density of a standard normal? Is 1 over square root of 2 pi e to the, oh, maybe I have to pay attention, right? Maybe I'll take it back. E to the square of 2 pi, e to, so yeah, e to a minus, right? D plus square over 2, okay? So the density part, because this is exponential of a negative number, this is always less than 1. Okay. So this whole number right here is less than 1 over square root of 2 pi. So you don't have to worry about this being large. But here you divide by S, right? Here you divide by S. And that's where it could get tricky. Because if S gets too large, that's fine. Then the gamma actually gets small, right? But what if S gets small? What if S goes to 0? Can the gamma blow up? Yeah, so actually I'm not so sure, but suppose you go for interview at one of the bank job, they might ask you this. Tell me the behavior. Let's say of gamma, of call option, when stock price is really low. How would you answer this question? And by the way, right, I mentioned this because this could be really an interview question. I'm not kidding. But second, though, is that a lot of people expect you to answer this not from Black-Scholes formula kind of thing. There's some other way to think about this, financial way, okay? And that's what what I'm interested in as well. Because looking at this, right, is not easy to tell. All right, but there is a way to tell by thinking about the behavior of the option price. And that's what they want to see if you know. How is the gamma when stock price is really low? Or for that matter, right? How is gamma when the stock price is really high? The answer is this. The gamma should be approximately 0 in both. And how do I know this? I know this from knowing the behavior of the delta. Remember, right? This is the picture of the stock. When the stock price is really high, what happens to the delta? When the stock price is really high, the delta is almost constantly 1. Emphasis on the constant part, right? Almost 1 and being constantly 1. But if something is a constant 1, what is its derivative? 0, right? Basically, delta is no longer sensitive to a stock price change. Same thing when the stock price goes to 0. What is the delta? Delta is constantly 0, right? Almost there. So delta is no longer sensitive with respect to the stock, right? So in other words, that's why the gamma are both 0 at those two values without doing calculation, okay? And that is something I want to bring up. This is right, and you could work out a calculation too. But, right, you see there's some limit. You have to be careful to take it when you do calculus here. On the other hand, the finance argument is very easy, right? I'm very sure that both of these are 0. So in fact, right, here's the stock. The graph of the delta and the gamma is like this. Here's the delta. Here's 1, right? And the gamma goes like this. I mean, it's not precise here, right? It's not like go directly to 0, but the gamma looks like that. Okay, and the gamma takes its peak where there was an inflection change in the delta, right? Because that's where the derivative of the delta is highest. Okay, that's where the gamma is highest. And guess where this is? This is roughly around K. So this point right here is where you say this is where the at the money point. And that's why it's interesting. At the money point at K, then the gamma is the highest. Okay, that means the delta is its most sensitive, not the option price. Okay, the option price is not sensitive here. It's not the most sensitive here. If you really look at the high sensitivity, then of course it's right here. But the delta is most sensitive here. Okay, and the gamma is the highest. Right? It's like a mouthful, right? You're speaking like a lot of like technical linguage, but any question? Okay. So point 4, right? Relating the gamma with respect to the gamma for call and put. How is gamma put compared to gamma call? So gamma put, right? So again, right, put call parity says V put minus V call is V forward, right, which is S minus K e to minus RT. So if you differentiate twice, right, then you got delta. But when you differentiate twice with respect to stock, what do you get? You get 0. So you get the nice fact that delta call is exactly delta put. Okay. So actually, right, if you care to write to graph, the graph of the delta, so let me say, right, this is delta call. Delta put, right, is exactly the symmetric graph this way. Sorry, it's -1, right? -1. So it's -1 to 0. So like this. So yeah, right, it's going to be just a shift from the delta graph of the other guy, like that. That's delta put. So because it's a shift, right, the gamma is the same. Okay. And right, so it goes without saying that you can figure out, right, we can generalize you know, this to the delta gamma of other any of other spread, right? For example, right, my favorite is the butterfly spread, right? K1, K2, K3, right? So the generalization actually is just by linearity. Is as simple as it can get. So V butterfly, right? Let me see, is V call K1 minus twice V call K2 plus V call K3. So that means that delta of V butterfly is delta of V call K1 minus twice delta of V call K2 plus delta of V call K3. That means the gamma of V butterfly is gamma of V call K1 minus twice gamma of V call K2 plus gamma of V call K3, like that. Okay, and anything else, right? As long as it's a linear combination of could call option, then you can just put that into, and then of course, right, once you have this form, then you just use, you know, what we know about Black-Scholes to obtain it. Question? All right. So I want to talk about the Vega, right, before I talk about something called delta hedging. So Vega. So Vega, right, is the derivative, like that, is the derivative with respect to the volatility of the stock, of the underlying. Okay. And so that's number one. That's its definition and symbol. Second, right, what's the calculation? So you see, so first, right, is the V, the call, right, is S0 ND V call. It's S0 ND plus minus K e to minus RT ND minus. So if you take the derivative with respect to volatility, whoops, then it will be, right, the stock price times the derivative with respect to sigma of the D plus and then this times the derivative with respect to sigma of d minus. Okay, and you work that out. But somehow, again, there's simplification going on, etc., until the final result gives you something quite simple, which is S0 FZD plus times square root t. Okay, like that. So what can we observe right away about the Vega? First, right, what about the sign? What about the sign, right? Vega is always positive, right? Second, how is the sensitivity of Vega with respect to, sorry, what am I saying here? What about magnitude? So hold on, right? So first, let's just carry this to the end. Vega being positive means, right, if volatility goes up, option price goes up. Okay. And so this really, right, is the point of what we said about last time. Like if we have two stock, right, with the same initial price, and whichever their percentage return, we don't care how they're related, however the percentage return is. But if suppose that the volatility of the first one is higher than the volatility of the second one, then automatically the call option price of the first one will be bigger than the call option price of the second one. Just like that. Okay. And of course, there are many things to, to explain this here, but the most straightforward way is probably by the Vega. Because, right, I mean, basically, if you hold this the same and you hold everything else the same, then it's almost, or it's exactly like you take the derivative with respect to the volatility. And so to show, right, this statement is the same as saying that the Vega is positive. Okay, so higher volatility means higher stock price, higher option price. Okay, I'm not sure. What about range of values? Can we say something about this? You mean S0 or 0? Oh, 0? You mean S0 or 0? Because there's still the S0 here, right? So, not quite. What you say don't make sense, because for example, S0 can be bigger than square root of t, right? So when you say S0 to square root of t, that doesn't make sense, right? So I guess first, right, I want to make this statement, but I want to caution you because it's easy to fall into this kind of trap. You want to make this, it seems like you make a statement like this, that the larger S naught means larger vega, and larger time to expiration means larger vega. Is that true? So in other words, right? Yeah, right. In other words, if you have an option somehow that the initial stock price is quite high and the time to duration is quite long, then the sensitivity to that option to the volatility, right, is higher than the same one, but with lower stock price and lower time to expiration. The answer, I think, is, I would say, not quite, or let's say that it's not clear, okay? Not quite clear. How about that? Why? The reason is you forget the most important piece, or not the most important piece, the last important piece, which is D plus. D plus right here also has S naught and T in it, all right, which can influence this in a way that you don't expect, right? Because D plus also as a function of S naught and T. How, right? Again, D plus is R plus 1/2 sigma square T, right? Let me change this to a plus, right? Log of S over T divided by sigma square of T. So you see, right, the T relation is a bit complicated because there's a 2T here, right? But let's look at the relation with the S naught. And so you see, if S naught increase, then D plus increase. That's clear. But if D plus increase, then the density of D plus decrease. Okay, so because, right, this is the normal density. So if you increase on this side, you go down. All right. So therefore, right, you have this pickup, but this goes down. It is hard to say. Okay, this is hard to say. So I will hold off here, right? I don't want to go to the deep end on this because again, right, it involves more analysis. But let me say one thing. This explains why we need what's the guy called? I would say is this. We need this. The partial of the vega with respect to S. That's what you're asking. And partial of vega with respect to T. Which, right, remember, I was telling you all those strange names. This is the second derivative of the option price with respect to volatility and then with respect to stock. This is the second derivative of the option price, first with volatility, then with respect to time to expiration. Actually, yeah, this has a name called Veta. This is Veta, okay? And I'm surprised that oh yeah, this is called Veta. Okay, and right, I already said at the beginning I'm not super interested in all these more exotic terms, but you see exactly that if you're serious about analyzing this object, you immediately see how, right, we see that these guys come up, right? Because you must know whether this is always positive or always negative to settle this kind of question. So here, right, by saying this, I'm assuming that the vana and the veta are always positive? I don't know that. I mean, I didn't look at the formula yet, right? But if you want to, right? So here, right? I'll just say this: need to look at the signs of vana and veta, all really exotic names. Is that okay? So I'll stop there. But so, right, it's enough for me that you know, right, that a vega is positive. But if you want to have higher or more deeper analysis, then you need this. Or you may need better financial intuition on how volatility affects the stock price and how it moves. It's not something I'm aware of. I have intuition about, so I don't have anything to share with you, right? My intuition kind of stops at the delta and the gamma, but the vega I just know is positive. But all right. Any question? All right. So next, I want to so relate this right to the put option clearly. What's the vega of the put? Well, so again, right, V call minus V put is forward. You see, right, there's no sigma on the right-hand side. So clearly, vega call minus vega put is equal to 0, or vega call is exactly equal to vega put. So we discovered two things, right? Vega of call and put are the same, and gamma of call and put are the same, okay? Which is quite important to keep in mind. And so, right, one thing we can say right away is because of this, they're both positive, right? It's the same thing. So in other words, if volatility goes up, then V call goes up. And V put goes up. Okay. And you can extend that to the vega of any spread. Question? All right. So for the last, I don't know, 7 minutes or so, I want to talk or start talking about the idea of delta neutral portfolio, gamma neutral portfolio. In fact, I mean, in general, you can say, insert a Greek name here, whatever that is. Okay. So that's one notion that people discuss a lot in the financial world. The second one I want to talk about is the idea of delta hedging. All right. So first, right, I guess it's obvious that the word neutral means 0. So when we say Greek name, whatever that is, neutral, what we mean is we want the portfolio, the Greek of that portfolio, the corresponding Greek of that portfolio is 0. Now, this is a portfolio of any asset, okay? Oh, sorry, any is too much, right? So what do we think of is in the portfolio? We think of the portfolio as consists of the following, right? Multiple derivatives could be 1, who knows, on, some on the same underlying. And then, of course, you have in the underlying itself, possibly cash. But cash doesn't change anything, right? Because cash is not a function of the derivative. So, and other variables. The only thing that cash, or what I mean is the money market. The only thing that it may affect is the sensitivity to interest rate. Because, right, cash or money market exactly grows with the rate of return R. So if you ever discuss rho, then cash may play a role. Otherwise, if you discuss like, gamma, delta, then cash doesn't play anything, right? Of course, that's probably what people kind of say when, cash carries no risk because it's not sensitive to any of these variables, okay? But of course, right, cash or money market account has the risk, as in like it's exposed to interest rate change. But again, right, usually interest rate is too small, so people never really care about it to begin with. Right, for example, when you have a delta neutral portfolio, what you mean is you want the delta of the portfolio to be 0. Okay, let's be concrete. Let's suppose you have a portfolio consisting of 1 share of call option and then X share of the stock. A very simple question is choose X so that, right, the portfolio is delta neutral. Okay. So the answer, right, the question is very simple. So you're saying something like this, right? At any time, the value of the portfolio is the value of the call plus X times the value of the stock. So obviously the delta of the portfolio is delta of the call plus X times the delta of the stock. But delta, remember, is the derivative with respect to the current stock price. So that's always 1. Yes. So in other words, right, if it's delta neutral, that means X is negative of the delta. And that explains why delta is something that you hear all the time, because it's exactly the amount of share you hold so that your portfolio, right, if it's going to only consist of this option, or, basically if you have multiple options and you just add all those delta together to be delta neutral, okay? And what does delta neutral really means for the portfolio, right? Delta neutral means the derivative with respect to the stock price, right, at that time is equal to 0. That means that a small change in the stock price does not affect the portfolio. Okay, so your portfolio is immune to a small change in the stock price. Okay. Now that's the introduction. We'll talk more about this next Wednesday. But one observation: this won't last forever. Why? Because the delta of the call option will move, right? As time goes on, stock price changes, everything changes, the delta will change. But right, this is the number of share you hold, so that will remain at this level. So this is why if you want to make a portfolio delta neutral, you must keep updating your portfolio every day or every, I don't know, hour or so. So usually every day, okay? At the end of the day, you have to rebalance your portfolio to make sure it's delta neutral again. So, right, it's delta neutral at the end of the day. From the next day trading, action moves, market moves, no longer delta neutral. You have to, right, rebalance your portfolio. So I guess the job of a trader, right, oversimplifying, of course, is to make sure that, right, you take the trading action to make sure that your portfolio is delta neutral. All right. So we'll go back to this next class. A reminder, next Wednesday, we follow Friday schedule, okay? So we still have class on Wednesday, but we'll meet at 1:40, okay, instead of 12. Instead of 12, right? Yeah, instead of 12, right? For next Wednesday. Exactly. But by the short, you assume delta is positive. So of course, which is true here for call option, but for some other options, delta can be negative, right? Who knows? For example, put. In that sense, you long, right? You long delta share of S. So short or long, right? But I think you're right, because when you say you short delta share of S, if delta is negative, short of a negative means long. But yeah, I mean, like, I would be careful to use the word short before I know the sign of delta to begin with. Yeah. Okay, see you. You too.